Insects such as flies and bees have evolved to become superlative flyers, able to perform aerial maneuvers that far surpass anything man-made. Inspired by these animals, the Harvard Microrobotics Laboratory has created a flying robotic insect the size of a fly or bee. This vehicle produces aerodynamic lift by flapping its wings, with kinematics that closely resemble those of flies. By modulating wing stroke motions, torques can be applied to control the flight of the vehicle. Though the wings produce sufficient force to lift off, the vehicle quickly tumbles because of dynamic instability. Much like a miniature fighter jet, continuous corrective maneuvers are required to maintain stable flight. Previous work has shown that this robot design can be made to fly stably, but the demonstration required external tracking cameras, meaning that the vehicle itself was flying blind. To fly stably and autonomously, the vehicle must carry sensors on board to perceive the world. Due to its small payload capacity, the robot cannot carry a traditional camera. Instead, we developed a simpler visual sensor inspired by insects. In addition to the compound eyes, most flying insects have three light sensors known as the ocelli. We reproduced the ocelli design by creating a sensor composed of 4 photoreceptors. Each sensor captures light from a large, diffuse area of the visual field. By comparing changes in sensor readings from different photoreceptors, the ocelli sensor can estimate angular velocity. We derive a model of the air mechanics of the robotic insect that shows how it can be stabilized using a damping action that is proportional to its angular velocity. We verified that the estimate of angular velocity derived from the ocelli is equal to its true value up to a constant and measurement noise, as predicted. We also verified that our model predicts the correct stability threshold for feedback gain. By combining velocity estimation from the ocelli with attitude stabilization, the vehicle is able to remain upright during takeoff flights. This is the first time a vehicle this small has flown using nothing but feedback from a sensor carried on board. Because the robotic fly is similar to flying insects, it can also be used to test hypotheses about biological flight control. Our results suggest how flying insects without gyroscopic organs, such as honeybees and bumblebees, could instead use the ocelli to stabilize their flight. This work constitutes the first steps toward autonomous robotic insects and motivates further developments in miniaturized fabrication, sensing, computation, control, and power source technologies.